Great. Okay, so thanks for inviting me. And I should say I really know very little about formal methods, so I'm looking forward to learning more. And I'll talk a little bit about how to describe agent behavior to people. Will also be in the context of reinforcement learning for the most part. And I'll start kind of more generally about explainable AI, and then I'll give some concrete examples and open problems that I see. So we see today many autonomous and semi-autonomous agents that are entering our daily lives. And what I'm interested in is how to improve people's knowledge and understanding of these agents' expected behavior. And this can be important for various reasons, such as trust or debugging an agent or choosing an agent. So there are different reasons why we'll want to know what the agents are doing. And this is difficult because people have a very hard time forming accurate mental models of technological systems. So we know this from the early days in human-computer interaction, when systems were even much simpler, that this is really hard for people to do. And now that we have agents that use deep models and so on, it's only becoming more difficult. So in recent years, there's really been a lot of growing resurgence of interest in explainable AI. And I think the most sort of popular form of that we see around is what's called interpretable machine learning, where we might have something like a supervised learning model, like a classifier, that outputs predictions, and then we can give an explanation, for example, in the form of which features contributed to the decision that this patient has or does not have the flu. But these approaches I want to highlight focus on these one-shot decision explanations. So it's not an agent that actually acts in a sequential decision-making environment, just a classifier that outputs a prediction. And I'm more interested in explaining the decisions in sequential decision-making settings, such as the ones that Sheila and Matthias were describing. And here there's less work. There is work in recent years on explainability in these settings. And most of them focus on explaining what I refer to as local decisions. So for example, on the left image, you can see a saliency map that shows which pixels the agent focuses on when it's making its decision, when it's looking at this game. This is one common approach. In the middle, there is something that's called reward decomposition. So if you think of having a reward function like Sheila described, but now it's decomposed into different factors. So you get some reward for example, think of a driving domain, you get some reward for driving in the right lane and some reward for keeping distance. And then you can decompose your reward and you can show people which components of the reward impact each decision. This is another approach. This is just a very high level overview. And there are also some causal approaches where you try to say, the agent performed this action because of something that happened in the past or because it enables something in the future, but this requires a causal model of the world. And these approaches are all explaining these local decisions, and they don't give you a global description of what the agent is doing. And in my group, what we've been working on recently is mostly this complementary question of describing the overall policy of the agent. Okay? So to this end, our approach is something we call policy summarization. So the key idea is that if I want to convey the policy of the agent to you, I can't tell you what it will do in any possible world state, right? So for example, here's an analogy to a human domain, saying that I want to describe to you how Michael Jordan plays basketball, what the capabilities and limitations of Michael Jordan are. I can tell you, okay, watch an NBA season, watch 81 games, and figure it out. But it's not really feasible, right? And the same is true for agents, if you think of an autonomous vehicle. So our idea is sort of like you would have a highlights video where you show kind of key moments. I can show you Michael Jordan making a shot or blocking someone or passing the ball. And the same way, I would like to show you key situations or key behaviors of an agent in order to convey the policy and important situations to you. And then the main question is, which behaviors should I show you, right? I have these 81 NBA games and I need to choose only a limited number of situations that I can show you. And so this is kind of the high level idea. And to make it a bit more formal, you've heard this in the past two talks, so I don't need to say much, but we're assuming we have states and actions and transition function and a reward function. So when we think of policy summarization, our input will be the policy of the agent that maps from states to actions, and some budget. And this budget can represent sort of the time limitation that the user has, or maybe it can be something that we can optimize for, but for now we'll assume it's a budget. And what we want to output is a set of state action pairs or a set of trajectories that demonstrate the behavior of the agent in some subset of world states, okay? So there could be an infinite set of possible world states, and we want to pick just K to show the user, right? And again, the question is, what should we optimize for? And we've tried several different approaches. I'll give you an example of one, the first one we tried. And our first attempt was to say, okay, maybe what we want to show users are important or interesting states. And what is an important state? So our intuition is that a state is important if the action that we choose to take in that state has a substantial effect on our expected utility. Okay, so think of Michael Jordan taking the last shot when they're 1 point down and there's 2 seconds left. If he makes the shot, they win. If he doesn't make the shot, they lose. So there is a large gap in the outcomes. Okay, and we can formalize this more computationally in a minute. So we'll assume that we have access to the policy of the agent, a simulator of the domain, and also access to the Q values, which also have been mentioned in the previous talks, right? Which tell us what's our expected utility from taking the current action and then following our policy. And one approach to think of an important state is to think about the differences between the Q values of different actions. Okay, so one naive measure you could think of is what's the difference between the best action that I can take in this state and the worst action. Okay, this is very noisy, it's very sensitive measure, but just as an example, right? So if there's no difference between the best and worst actions, then this state is not really interesting, right? It doesn't matter what I'll do, everything will be the same. So just to give you an example from Pac-Man, which is a domain we used in our experiment with people, and the state here will be important because if Pac-Man turns towards the ghost, they will die. And if not, they can still get many points. But this state is not important. Maybe some actions are better than others, but even if I turn right, I can still go back left and nothing happens. Okay, so that's sort of the intuition. Hopefully it's semi-clear. And then we have an algorithm that creates this policy summary, we call it highlights, basically by running simulations of the agent and collecting states, computing this importance score, and taking the states with the highest importance score. Okay, you can do it online or do it offline, it doesn't really matter. And then you would get the equivalent here of Pac-Man as Michael Jordan, and you can see it eating power pills and escaping ghosts and doing all these things. So this is one idea. One addition we did for this to make it slightly better. If you notice here in this summary, the situations that we show are very similar to each other. They're all in the corners, sort of. And so the other criteria we added was of diversity. So maybe I want my summary to include important states that are different from each other. And when we add this, we get somewhat better summaries. Let me briefly talk about how we evaluate this, because I think this might be interesting to you since now the evaluation requires people. So what we did here is we created an agent selection task where we show people summaries of 2 alternative agents. And we ask them to say which agent do you want to play the game for you, and they get compensated based on whether they chose the better performing agent. Okay, and we can create this task such that we have a ground truth. So we created 3 levels of agents simply by training them for a different length. So we have the low performing agent, medium and high. And then we compare different summary approaches. So we have our algorithm, we have a random, which is not really random, it's based on frequency. So I sample states as I run the simulator. So states that are more common will have a higher likelihood of being sampled. And the third approach was just showing the first trajectories that the agent encounters. And they all use the same budget. And this is like you watch Michael Jordan until you run out of time. And we ran an online experiment where we had people do basically 9 comparisons. So for example, the low versus medium agent with highlight summaries, the low versus medium agent with random summaries, and so on. So they do all of the pairwise comparisons. And now we have a ground truth for whether they identify the better performing agent. And what you're going to see here on the y-axis is the correctness rate. So if they're just guessing, this would be 50%. And this will be decomposed into 3, depending on the comparisons, which agent played which. So for example, the low versus high agent should be the easiest because there is a large difference between them. And the colors will be the different approaches. And happily for us, with the highlights, people were able to identify the correct agent, the better performing agent in the majority of cases. And some interesting observations here are that when they were shown the first trajectories, if you see the low versus high comparison, which should be very easy, it's like a very bad agent versus a very good agent. People that saw just the beginning of the game actually did very poorly. They only got it in about 10% of the time. And we asked them to explain their choices. And what they said was that it looked like the agent, the good agent was taking risks, and they didn't see the rest of the game. So they didn't know that this agent can actually do this. So we saw this. We also, I won't show it, but we also had a subjective questionnaire where we showed summaries of the same agent, but different summaries. And we asked, which one do you think conveys better the agent's behavior? And there also people preferred highlights. And so just to recap this idea, the idea is that we want to demonstrate key behaviors of the agent. I'll briefly mention we have other approaches to do this too. One looks at optimizing for policy reconstruction. So if my goal is to be able to complete and predict what the agent will do in new state, we use things like inverse reinforcement learning to choose the states that will allow this. And recent work from Yotam, one of my PhD students, looks at if our goal is to compare different policies, so different players maybe, then it looks at disagreements between the policies. We show states where the policies diverge. So this policy summarization approach, which is really just one approach for globally describing the behavior of the agent. And kind of popping up a level and to finish, I think there are many interesting open problems in explainable RL, probably many more than what I have on this slide. And so one thing that I think is being sort of neglected is that we're explaining the policy, but people might not even understand the underlying Markov decision process or the environment. So it could be interesting to think of ways to explain that. Also, most of the work is in this visual Atari game, highway environment domains, and less clear how to show things when it's not so visual. A very interesting question that I've been talking to Guy a bit about recently is kind of the level of granularity. So people often think at the level of an action. Why did you take this action? But maybe people will actually care more about the behavior, right? Like something that's a sequence of states and not just a single state. And things that are more on the human side, one is to adapt explanations to users. So one thing we saw in our experiments is that people come with various prior assumptions, and it's not like they're coming with this blank page and we're explaining that they have their own thoughts. So we need to account for that. Another very interesting direction that Guy and I are actually collaborating on now is interactive explanations. How can we answer queries from the users rather than just showing them whatever we choose? And I think evaluation is always a key challenge here because we really care about people's performance and it's a bit hard to do. And so thank you, and I look forward to the discussions.